Awesome. So hey everyone. Thanks for joining in for this week's talk. This week we have Natasha to give us a talk on RL fine-tuning of LLMs. Just a quick intro for Natasha. So Natasha is an assistant prof at computer science and engineering department at UW, and she's also like a senior research scientist at Google DeepMind. She works on a bunch of topics, but something we are pretty like we really want to know more about is like on social reinforcement learning in multi-agent and human AI interactions, and that's what much of a talk would still circle around. She did her PhD at MIT, and like she's won various awards like Best Demo at NeurIPS, Honorable Mention for Best Paper at ICML, and Outstanding PhD Dissertation Award. Um, I mean, she has a bunch of accolades, so I don't want to get into all of
Yeah, you don't need to
yeah,
do the
but
whole
I'll hand
yeah.
it over to Natasha and like she can talk more about the work here.
All right, thanks. And thank you so much for having me. I'm excited to be able to present to you guys. And like I said, I love getting questions throughout or comments and making it more interactive so we don't fall asleep. So please do interrupt me. As you can see, I've crossed out social reinforcement learning. So instead of giving you the spiel about like what my lab does and multi-agent and social learning, I want to really hone in on a subset of what I do, which is about RL fine-tuning of LLMs. And especially because obviously, if you're following the news and the hype, you probably have seen the DeepSeek R1 paper and what a big change this has led to and what a big hype storm this has kicked off. How many people have read the R1 paper or like at least seen this on Twitter? Okay, obviously we don't live under a rock. Okay, great. So it's pretty exciting. I really like the paper, but it made me really want to discuss it today. But even though it's so cool, I just have to share a lot of bad takes on Twitter about this. So I've seen people saying stuff like, "It seems RL might finally be starting to work for LLMs." And this is just such a bad take, right? Because if you remember, like O1 is also RL. But even going back to the reason we're actually in a mega AI hype moment is ChatGPT, right? And what was the key differentiator between ChatGPT and previous LLM work? It was also RL, right? So it was RLHF. So RL is such a powerful tool to train language models. Even though the R1 paper is amazing and I love it, it's not that we're now in the RL era. We already were, right? And, just harking back, if anyone has forgotten the original Instruct GPT paper, if you look at this, the RLHF tuned model was preferred in that paper by humans over a model 100 times the size. So the authors of that paper conclude investing in RLHF fine tuning is more cost effective than continuing to scale. And so we kind of see this whole thing repeated again with R1, right? Which is like, oh, we can use like much less compute and it works so well. Well, we also saw that with RLHF for ChatGPT and for InstructGPT, right? And just remembering like RLHF is what makes ChatGPT and other models actually chat, right? If you just do supervised learning on all the data on the internet, you don't necessarily always engage in conversation. It's the RL fine tuning process that elicits that behavior, right? Um, but the reason I wanted to open with this stuff about the DeepSeek paper is I really loved it. And in part because I think it reads like a little bit of a love letter to RL. So I'm just pulling out some quotes here. Like they say, behavior such as reflection, where the model revisits and reevaluates its previous steps, exploration of alternatives, arise spontaneously. Behaviors are not explicitly programmed, but emerge as a result of the model's interaction with the reinforcement learning environment. It's a captivating example of how RL can lead to unexpected and sophisticated outcomes. And rather than explicitly teaching the model on how to solve a problem, we simply provide it with the right incentives and it autonomously develops advanced problem solving strategies. Right. And so when I'm reading this, like I'm kind of harking back to why I actually got into RL in the first place, which is I was doing something completely different when I started my PhD. But I remember going to my first NeurIPS, and I actually can't find the exact video I saw at that NeurIPS. Maybe my memory has, I don't remember it well enough. But basically, it was a humanoid robot trained with deep reinforcement learning with no other explicit behavior cloning or any other hints about what it was supposed to do. And it could learn really sophisticated movement patterns just by optimizing the RL objective. So I found this video of a humanoid doing a backflip. The video I saw was not a backflip, But it just made me get so hyped and so excited about the power of RL to actually learn such complicated behaviors if you just set up the incentives correctly and let it go. And so I think this paper is really echoing that sentiment. And so that's why I wanted to just spend the talk today talking about, yes, RL does work also for language models if you set it up correctly, and kind of going through, I have a bit of a stake in this as well, because I was actually doing some very early RL fine tuning of language models way back. So I'm going to kind of talk about how I started in that and like where it led to, where we are now with RLHF. Then some more recent work we had from NeurIPS this year on pluralistic alignment for RLHF, and going into some future work on why RL researchers should actually be caring more about NLP, because it's surprising that sometimes they really distance themselves from this stuff. And I find that confusing. All right. So just jumping into this, I want to talk about like the early OG stuff I was doing almost a decade ago now, which was this music generation. And so what I was trying to do is I was interning on the Magenta team in Google Brain, and we wanted to, train models that could generate music. But if you trained, big language models, quote unquote, then on a bunch of music data, this is how they sounded. So not very good. Probably not something you want to jam out to. The models then had a lot of issues. And one of the issues was that the compositions that they would generate lacked structure, right? So it wasn't able to adhere to what we know would be like a reasonable music structure. And so the idea that we had was, could we use RL to enforce rules of music theory, like impose that structure via rules, like a game-based reward? And so we were going to pre-train on data and, fine tune with RL according to some reward function. And this was an idea that was around at the time. So people were doing this for translation. They would train on Blue Score. They were doing this for dialogue generation. Like Jiwei Li had a bunch of stuff on like early RL training of dialogue models, if you're not familiar. But there's a problem with this general paradigm, which is if you just train on data and then you fine tune with just the RL objective, it actually doesn't work that well. And the problem is you end up with, at the time we thought of it as catastrophic forgetting, right? Basically optimizing for RL erases what you learned in the first task, which is the data. But it's also a problem that your RL function is probably, your reward function is probably not perfect, right? So our music theory rewards could structure the composition, but not actually generate enough novelty and interesting compositions. And it's still the case with, RLHF today and human data trained reward functions. Your reward function is probably imperfect. So you get this kind of like reward hacking behavior, and that isn't exactly what you want. The model can move away from generating plausible generations to just over optimize the reward function very easily. And so what I was seeing when I first did this for music generation is, according to my reward function, apparently the optimal composition is just to play middle C over and over and over again. So it didn't sound too good. So that wasn't working. So what we said was, hey, instead of just pre-training and fine-tuning with RL, why don't we keep around a fixed copy of the model that was trained on the data? And we're going to call this our data prior. Now you might think of this as your reference policy. And we're going to constrain the RL updates to make sure you stay close to that data prior. And we're decided to do this with KL control. And so this is essentially the first paper to say you should do KL control from a pre-trained data prior that was trained on the data. Previously, KL control had only been done for like maintaining minimal divergence from like a uniform distribution to increase randomness or something like that. And so what we said is, okay, instead of just maximizing rewards, which is what you want to do in RL, we're going to also minimize divergence between your RL policy and your pre-trained prior, your reference policy that you train on the data. We did this with Q-learning, but it amounts to basically just subtracting the probability, the log probability under your policy, and adding the probability under the data prior. And we did some fancy stuff to integrate this with like existing KL control techniques. So there was a bunch of KL control techniques that, like I said, minimize divergence from like a uniform distribution. So we kind of integrated this with all of these, but the key idea here was you're just using this reference policy. And what's cool is that if you compare, so we'll listen again to this but if you then train RL with this KL control technique, this is what you get. So it's catchy, right? So like a little more interesting. We actually had a piece of, I think it was like a MIT Tech Review or some news article came out and called it like toothpaste jingles. So is it like solving like AI generated music? No, but it's doing something. It was such a remarkable difference, like when you could actually set it up properly to maintain this information about the data, but optimize the RL objective. Like it was really tangible. And I didn't include this, but we had like a human study that evaluated the things. It was significantly better. We also applied this to drug discovery. So basically, you could train a sequence model on a bunch of known drugs where you encode the drug as like a sequence of molecules. But then when you try to sample from that, the chances that it decodes into a valid drug are pretty low, like 30% chance. And you might also not just want to decode drugs, you might want to optimize the drugs to have certain properties like synthetic accessibility, like how easy it is to manufacture, or whether it looks like it might affect the human body. So they had different metrics here. And so we did this RL fine tuning to do drug discovery. And this approach actually got picked up by benevolent AI and ended up being like the predominant drug discovery approach for a while. So it clearly worked. This thing also was part of the, oh, sorry. Stop. Okay, this was also best demo. I'm going to move on. But the cool thing about this is still used today. So if you follow like the OpenAI series of work on RLHF, they still use this KL constraint idea. Google uses it. And actually, it's also in the DeepSeek paper. So the regularized RL update is still from this like very early music generation stuff, which is fun. But what's cool is we actually followed up on this to do some early work on training dialogue models with human feedback. So I think this was the first paper to do that. So what we did was we actually built a web interface to put dialogue models online, have people talk to them, and save that data and try to use the way people were responding to the models to train the models with RL. Now, we did this a little bit differently than modern RLHF. We did it with offline RL. But a key hypothesis we wanted to test was whether you could learn more effectively from the type of binary labels that are used in modern RLHF, or whether it would make more sense to learn from implicit cues in the conversation itself. So we looked at things like conversation length. How long did the person bother to spend talking to the model? We looked at the sentiment of the user's response. So like, look, you're looking at pre-GPT, like this is like a hierarchical LSTM situation going on, like a seek to seek LSTM. The model is pretty bad. It says like, hi, sorry to hear. But the user is able to respond like, that doesn't make sense. And we can detect that that's a negative sentiment, right? And that could serve as a potential reward signal to train your model. And it's like it's implicit in the conversation itself, so you don't have to collect extra feedback data. The user does not have to go out of their way to give you labels, right? And we were able to show that, of course, the KL control version works better than the classic RL version. Okay, we know that already, or we now know that already. Timelines are confusing. Whatever. So the point is, we actually validated this thing though, which works better, training on these manual upvotes, which the user has to sort of go out of their way to provide, so it's inherently more sparse, or training on signals inherent in the conversation itself, like sentiment. And it turns out that in maximizing something like user sentiment leads to higher perception of conversation quality than doing something like these manual upvote downvotes. So I think this is really interesting. And like still to this day, I haven't seen a paper that does this same idea, but with like more modern RL techniques, like learning the reward model and optimizing online versus doing offline RL. So I think there's still some rich ideas here that now that everyone's getting hyped on RL for LLMs, you could bring back or start building on. Yeah. Oh yeah. So this is better than manual feedback. We said that. Another thing that we did way back in the day, and also Ji-Wei Lee was doing way back in the day, is self-play for language models. So you have the model talk to itself, a copy of itself, and you get synthetic data simulating the human, and then you optimize with RL. So the LLM is providing the environment. You optimize with RL. Still to this day, I haven't seen a paper that does online multi-agent RL fine-tuning of modern LLMs, which is crazy because there's obvious reasons why you would want to do this. But I think the reason is it's computationally expensive and it's hard to build the infrastructure. But this is actually something we're now working on in my lab, trying to do this with self-play again and bring it back. But yeah, it works good in 2019 with smaller models. So we see like our VHRL model, which is trained using self-play, is now achieving even higher conversation quality just by training and simulation with these same sentiment-based rewards, but with this self-play technique. So I think this is a pretty exciting direction that we could go in now. We also show that this is able to reduce the toxicity of the model, which is a thing you might really want to be doing if your models are trained on the entire internet. So I think this is a promising direction to go in. But that's all the past. Let's talk about the modern RLHF era that we're actually in. So again, just harking back, ChatGPT is really what kicked off why the New York Times keeps writing about AI, right? So ChatGPT, I hope I've convinced you like this RLHF model or paradigm is really powerful. It's even still used in DeepSeek, although they seem to not like the fact that they have to use human reward models. They're like, we resort to having to do this. But I think it's still an important step, right? If you just train on the entire distribution of text on the internet, you do need some human fine tuning to understand what is appropriate. How do I actually interact with humans? It's critical. It's the only way, really. Well, I guess not the only way, but the predominant way we have of making sure these models aren't just saying a bunch of toxic stuff that they learned from the internet, right? So we want to make sure they're not using inappropriate language. We need this fine tuning step. And we see, like, even in this original paper, it's reducing hallucinations, it's doing this kind of thing. So it's a critical step. To give you some background, which you probably don't need on what it is, you collect a bunch of human feedback data, which says this response is better than this one in terms of helpfulness, harmlessness, appropriateness, whatever. You train a reward model to be able to predict what the human would say on a novel sample. This is something that my early offline RL stuff doesn't do. You then fine tune your LLM with RL according to the reward model. And of course, profit. That works really well. It's great. But it's interesting that it's still, like, under the hood, a pretty simple recipe technically, like from an algorithmic perspective, right? It's this KL control thing, and it's this reward model from human preference data. So let's spend a little bit of time diving into that BTL reward model. So the BTL reward model is basically just saying humans are going to rate which of two model outputs they prefer. And this is motivated by this idea that humans are actually quite bad at giving absolute ratings, like absolute magnitudes, and they're better at making comparative judgments. And then you learn this essentially maximum entropy inverse RL model, which says the probability that they're going to prefer one state to another state is exponentially related to their underlying hidden reward function for that state, normalized by the reward function for the other state. So this is just like a softmax function, but it's also using maxent IRL. But it's essentially also coming from like 1950s work on, behavioral economics and stuff like that. So that's why there's this whole resurgence of, people doing social choice theory for RLHF. But it's interesting we're still using this BTL model because it has some issues, which I'm about to go into. So when we think about aligning language models to quote unquote human values, what do we mean by that? Like, who are we actually aligning to, right? The problem is that the way this actually works is and the big difference in getting RLHF to work, if you go back to the series of papers on RLHF from OpenAI, they tried to do this originally in one of their first summarization papers, and it wasn't working that well. And the key difference between that paper and the next one was that they realized they had to really heavily curate the human labels. So what they did was they trained their raters to have very high inter-rater agreement with OpenAI researchers, what the OpenAI researchers would have said for this rating. And they had like a Slack chat so they could like give real-time feedback to the raters so that the ratings were consistent and stuff. Like maintaining consistency in the human ratings was a key part of getting RLHF to work, right? And so essentially the values and preferences that are decided for what is appropriate for, ChatGPT to say are decided by OpenAI researchers. And, these are computer science PhDs that are not trained in sociology. And it's interesting that like this model is deployed to 100 million monthly users or more. I guess Gemini has like 300 million monthly users, so presumably OpenAI has more. Maybe I'm out of date, but like this is reaching so many people, but the decisions on what it's allowed to say and what's appropriate are just like this very restricted set of people, which I find strange. And then, of course, the training data for these are often coming from OpenAI customers. So it's not clear that their goals in their app that they're building align with actually like human flourishing or providing appropriate responses. Excuse me. So, this has led to increasing calls for more pluralistic alignment of language models, right? So this is a paper coming out of UW. Yejin as a senior author, Taylor Sorensen as the first author, basically calling for ways to incorporate alignment to more diverse groups of users rather than just this like heavily curated group of raters. So in the real world, people have all kinds of different preferences, different cultural values. We shouldn't be just erasing those and aligning to one set. We should be able to incorporate these more diverse perspectives. So you might say, there's different ways of thinking about this. You could say, if there's different values, I could just say all of them. I could cater to whatever particular thing the user wants. Or I could just develop better ways to model the distribution of things that users might prefer. So this is a more technical approach. How do I even understand what are the different preference functions in the wild when there's a massive group of users? And so what I'm going to talk to you about today is an approach to accomplish this distributional alignment. And let me give you a little bit more motivation about why we need this. So this is a really nice paper that came out. It's on distributional preference learning. And it looked at whether the BTL model as is can even accommodate feedback from diverse groups of people or people with divergent preferences, let's say it this way. And the answer is no. So they give a really nice example in the paper that if you were, say, a chatbot that was trying to be used for, like, let's say a college for information about admissions for that college, right? The college predominantly serves high socioeconomic status, wealthy people. So if you were to collect RLHF data on the preferences of the users applying to that college, the majority of users would say, I don't need to see information about financial aid. I have a slight preference to just not see that. But for a small group of users that need financial aid information, it's very high utility that they get it. But if you just train BTL on that data, you would learn a model that never shows information about financial aid. Because they show in this paper, it's going to do like a board account majority voting of the preferences. And so if a minority group is outvoted, it will just not cater to their preferences. So this seems bad. And a part of this is that the BTL model has no way to actually learn about the underlying magnitude of people's utilities when they're giving preferences. Right. So the fact that the people who need the financial aid have this very high utility for seeing that is not accounted for by preference data. It can learn potentially infinitely many reward functions of different magnitudes, and there's no way to compare across these different groups. So that's a problem. So we're going to try to introduce a solution, which is we're going to call variational preference learning. So we actually look at this both in the language context and in the physically embodied setting. But let's also think about like why we might have divergent preferences in these settings and then why we might need to respect them. So in language, you might see each user has different preferences over their writing style, the level of expertise they're comfortable in receiving when they ask for like a scientific explanation. They might have preferences for how concise explanations should be versus verbose. But I think it's quite obvious when you move to the embodied setting why you need to do this. Like, let's say I want to make a household robot that can help me clean up my house. Well, it needs to be able to personalize to where I put my stuff. Like the average policy of just putting away stuff in my house is just complete failure. Right? So it just doesn't work unless you do some personalization. And we'll show this here. So let's look at this example embodied setting. So we constructed a task where we're in this like grid world. We're trying to get an agent to move to one of these two goal locations. Some users prefer that the agent moves to the bottom right. Some users prefer that the agent moves to the top right. if you just take those preferences and put them into the BTL model, what you see is it just learns to average the modes of the two groups of preferences. So it learns a reward function that's essentially inaccurate for all users. Your robot is going to go here. Nobody actually wants that. So it's essentially completely useless, right? So even if you don't care about these ideas of like respecting the values of diverse cultures, which I hope we do, but even if you don't, you still need this to make your model accurate. Otherwise, it's just going to give you bad performance. So it's actually a really critical issue to address if you start trying to get data from more diverse users. And I think this is critical. Like, I don't want to say something too out of pocket, but I noticed that like OpenAI has followed up with, so this is a recent spotlight presentation at NeurIPS. So students, Shriyash, Yaming, myself, Abhishek, Hamish, OpenAI like reached out to all these students and me to like try to give us a job after this paper came out. So I think it is something they're interested in, because if you look at the API, you are actually constantly asked to give preferences all the time. So each user is giving diverse individualized preferences over which response they prefer. And if you just take all that data and shove it into the BTL model, it's not going to work well. So you actually do need a way to start learning about people's different preferences and modeling those more effectively. So again, that's what this is trying to do. So yeah, this VPL thing, what we're doing, the idea is BTL gives this like incorrect reward, homogeneous preference model, ignoring minorities. We're trying to fix those issues. And it's this pretty simple idea. What we're going to say is, given a few preference labels from a particular user, we're going to try to infer a latent user vector Z that's going to encode information about the underlying differences that cause them to have different preferences. And then we're just going to train a Z-conditioned BTL reward model that's able to recover the multimodal preference distribution for different users. So essentially, this is the reward function for one Z. This is a reward function for a different Z. We have this example of like users that may prefer more concise or more short or more lengthy explanations. And so we can see that this would actually capture that and understand which user prefers which. So how do you actually train this? Okay. We basically introduce a Z-conditioned BTL model. So the Z is going to give you the degree of freedom you need to account for the fact that different users have different reward functions. But of course, optimizing this is now intractable. So you would need to marginalize over the unobserved Z. So we introduce a variational posterior and evidence lower bound. But essentially what this amounts to doing is learning a VAE reward model. So I'll show you how we do this in the language context, but at a high level, what we're doing is you're given a bunch of preference data of like state pairs and the preference. You encode that into the Z, and you use your reparameterization trick to make sure the Z looks like it's sampled from a normal distribution. And then you learn a decoder that predicts the reward function condition on this Z. So pretty straightforward. A little bit tricky to get working in the language setting, but I'll say more about that. But then once you have the Z, you can obtain personalized policies by just using your reward model as a normal RLHF, but you use a Z condition policy. So you take the Z that you inferred from a few preference labels and condition on that and train that with the reward function. I've been talking for a long time straight. So does anyone have any questions at this point?
Hi, I actually have a kind of a math question. So I'm not super familiar with this variational learning math, but I want to ask, in this framework, is there an assumption that the user preference may follow a Gaussian distribution? Like, I'm not sure if that's the assumption here, but if it is, I feel like it may not be super realistic, because I feel like people may have different preferences and then they may diverge rather than be similar around some mean value. So yeah, I want to ask about that.
It's basically saying, so this is like classic VAE stuff. So it's not new to our work, but it's basically saying that this Z vector, which would be like a many dimensional vector, each dimension is independently and normally distributed. So like the Z value you have for a particular point in the vector, like a particular dimension, is going to be normally distributed. So you can think of it as like all the vectors fall within some ball. But when you train the model, you have a coefficient that amounts to how heavily you regularize it to make those vectors look like within that KL ball. And that's a parameter you can play with. But it's not saying that the preferences. Yeah, it's not so clear to say that just like all preferences are normally distributed. It's actually the vectors that are normally distributed in a big ball in like a high dimensional space.
So you're saying, although the vector is in the normal distribution, it's possible that it can model very complex preference.
Correct.
Oh, okay. Thank you very much.
Nice. Yeah. Thanks for the question. Any other questions, or please interrupt me also if I keep talking. Okay. All right. So moving right along, how well does this actually work? So the good news is if you just do this, which is a very straightforward thing to do in this robot land, you can see that VPL is able to correctly recover something like the ground truth reward function of the original labelers. So we see that some users prefer the bottom right, some users prefer top right. And so that looks good. We're doing this multimodal reward modeling. That's nice. It's not mode averaging anymore, but there's a problem. So the issue is, as I mentioned before, the BTL loss doesn't give you any information about the scale of the reward function. The scale is arbitrary. Not a problem in vanilla RLHF where you essentially have a single user. But if you now care about modeling the reward function of many different users, what you'll see is that we see the reward function for this user group. They think the maximum reward of getting to the goal is positive 450. And the reward function for this user group, it inferred as negative 400. So essentially, it's completely not comparable across users. So why is that a problem? Well, if you can't compare utilities across users, now we actually can't do the thing we wanted to do, which is detect if users' preferences actually diverge for a given state. Because if the magnitude of the rewards are different, that doesn't mean that they actually don't both prefer one outcome or the other, right? So it's not actually useful in that sense. And it's really hard to optimize. Now you're doing this like multi-objective optimization where depending on your value of your Z, you might be optimizing vastly different scales of rewards. So you might focus more on catering to the preferences of a particular user just for like numerical weirdness issues. So that's bad. This is not the equitable thing we were aiming at. So how do you actually solve this, right? We borrow this idea from this SPO paper, Maximum Minimalist Approach to Reinforcement to RLHF, to basically just treat your reward model as a classifier. So you now have a slight downside, which is your reward model has to always condition on two states, like two utterances, and predict which one is preferred. So you can't just like evaluate the reward without the other state. But it does solve this issue where now everything is normalized to between 0 and 1. So that's nice. So what we do in practice is we have to sample like other possible utterances that you would evaluate and classify whether the current utterance is preferred to that batch. So this resolves that issue. And we see that now when we apply our method in simulated robotics tasks, so we make a bunch of tasks of increasing complexity to say like, okay, you might have different locations as a maze, as I just showed. You might have different preferences where you place an object, either in a robotic manipulation task or in a home, stuff like this. And what we see is that compared to vanilla RLHF, which is this yellow line, the BTL model, and compared to DPL, which I mentioned already, ours is sort of the only method that's capable of actually catering to these different preferences. So what DPL does is it can tell if preferences are diverging because it sees like a high variance in the reward model, but it's not able to actually like adhere to the diverse preferences of different users, whereas ours is the first to be able to do that. So we actually can kind of solve this issue in the robotics task. That's nice. In the robotics setting, we do experiments to see like, can we generalize to unseen users? So this is actually accomplished by, because it's a VAE, you get some nice, oh, we got a question. Sorry, I see a raised hand. Yeah.
Thank you. You can finish and then I'll ask after. That's
No, it's okay. Go ahead. I can, yeah.
Yeah, so over here you say that like in each task, different users obviously have different preferences, for example, where an object belongs, but then what is like, is there a ground truth or like not a ground truth, like an initial state that, you know, a model will come in, or is it just randomized? Suppose you have like 3 different places an object can be placed by a robot. Is it just randomized in the very beginning, and then based on user preferences, it learns over time? Or I guess, what's the initial placement state?
Yeah. So initially you might see like the robot is like, you see this green dot might be the start state of the robot, but then it doesn't know what user it's interacting with. But what the robot is going to get is some preference data from the user. So the user will say, I prefer that you are in this state versus this state. And then once you know that, that gives you a good clue that it's probably a blue user. Does that clarify?
But then again, this is you're basing it, I guess, like on like certain groups which you have prior information about. So you get information from lots of people for their preferences, and then you just group them, and then you have distinct groups. But then will it learn over time that maybe, for example, if you're thinking two halves of the room where red is top half, blue is bottom half, if the user says, I prefer, a little bit to the bottom of the green position than the top, initially it'll say I'm blue, but then will it, I guess, create a new group if the user prefers the left bottom versus the right bottom over time?
This is a very insightful question. So if you had never in your training data seen a user that wanted to go to the bottom left, it's unlikely that, given that you'd only seen bottom right and top right, you could get there. However, if I had seen a bunch of users with preferences for all sorts of different goals, which by the way is the next experiment I'm going to show, then I can adapt to a new user because I can interpolate in that embedding space of user preferences. So you could say like, and actually maybe I'll just like, well, I won't skip to that, but imagine like we'd seen sort of all different preferences of, are you seeing my mouse, by the way?
Yes.
Awesome. Okay. So we'd seen like preferences covering this possible space, but not every single location, but we'd seen like one here, one here, one here, one here. We could say we have a Z representing this position, this position, this position. You could infer a new Z that's in between them, and it would generalize. So as with any machine learning, interpolation between the existing users and the training data is possible. True extrapolation, like way off the distribution of users you've seen, might be hard. Does that make sense?
Okay. Yeah, that makes sense.
Okay. Yeah.
I have a quick follow-up question on that as well. Just trying to understand the expressivity. So like I think in the first case itself, I see that there are two possible groups that you're trying to work with in this setting. When you look at the mu and the sigma for the user vector, basically, how big were they? I'm trying to understand, like, for two groups, how much expressive power do you need? And my second follow-up question here is, like, this is just one dimensional, right? But maybe you just replace that red square by a triangle. So now I have two dimensions where I have colors and I have shapes, and people, like, we want to extrapolate between these two dimensions as well. Like with ChatGPT, like, people prefer longer answers, but people prefer answer with citations, and there are multiple dimensions.
Yeah.
Did
Nice.
you explore that, or what are your thoughts on that?
So we do have some results to that effect. Well, I guess this is kind of the best thing, where we have like 100 different users that all have different preferences for like object locations, and like there's a bunch of objects that they want to put away. So you can imagine the combinatorial complexity of like 100 different users want to put away 5 objects in different orderings, right? So we do explore that. As I'll get to the language results, our language results, we have to use kind of existing preference data sets. So we basically just have like harmfulness and helpfulness as the user types, which I think is a weakness of this work. So I'll talk about that in a bit. The PRISM data set, for example, just came out that actually collects much more well, it's a small data set, but like from 200 different countries, people talking about all different topics, deliberately meant to be controversial. So I think a nice follow-up to this work would be to say, like, can we model PRISM with this? But yeah, I think in theory, yes, but we haven't done that experiment. So yeah. But yeah, so, okay. This thingy says, oh yeah, so there is actually a cool way we actually get generalization to new users. So the reason, I was going to say, so it's a VAE, right? So essentially your Z's you actually have a probability distribution over your z's. One, that gets you some nice properties, but you can also sample z's from that Gaussian and then practice training a policy to adhere to preferences anywhere in that space. So you can essentially have practiced adhering to all the preferences in the embedding space. And that's what we do to get like generalization to unseen users. So we sample a bunch of z's from the prior and then train the policy. And so then when we get a new user that again might be like a new location we hadn't seen before, but we've practiced it adhering to that preference in simulation. So as long as we can correctly infer the new z, we can accommodate it. I hope that made sense. Stop me if it didn't. So yeah, so we can do that. We can scale up to like 100 different users. The cool other property you get out of this being a probability distribution over the z's is that now you can measure uncertainty in the z. So you can say, I've had a few queries, I've had a few preferences. What is my uncertainty in being able to accurately predict the z for this user? And using that uncertainty estimate, you can now do active learning. So you could say, what is the set of queries? What, two pairs of utterances should I present to my user to most reduce my uncertainty in predicting this user's z? And so we can show that we can find this like minimal set of queries to accurately infer the z for a new user. And I'll show some results about this. Oh, I'll show some results about this right now, which is, if you do this active learning procedure, then you actually can accurately get the same performance in only 4 queries that you, without doing it, would need 8 to take. So this really reduces how many preference labels you need to get from a new user before you can infer their z. All right, but how well does this actually work in language model then, which is significantly harder? So to be able to do this, we're saying that we need to train a reward model that's going to take a bunch of preferences from the user and embed it into a single vector, z. And the problem with trying to put a single vector embedding into a transformer is it's hard. It doesn't really work. The magic you get of transformers is they get this quadratic computation over the length of the input rather than being forced to compress everything into a fixed size. And papers that have looked at trying to introduce, bottleneck embeddings or embeddings of transformers often see these big performance reductions. So how are you going to get this to work? So we had to play with this for a while. We did a bunch of different tricks. There's more in the paper. I'll highlight a few here. We actually had to train the reward model for more than one epoch, which in RLHF is kind of atypical. But we found that you essentially first have to learn to encode users into the Z embedding space, and then you kind of learn how to model rewards for that Z embedding space in multiple epochs. The data augmentation trick turned out to be really important. So let's say I have like 8 preference labels for a particular user. What we do is we resample many, many different subsets of those 8 labels to provide different contexts to be able to predict the reward function of that user. So you can resample those same 8 samples many, many, many times to learn more about that user. And then we use a special reward model architecture. This is our LLM architecture. So this encoder LLM weights are fixed. We take the states, like the utterances that we're encoding, and take the last token embedding. And then we take, using that fixed thing, we embed both of them. We pair it with the preference label and have a pair encoder that we apply across every single pair of preferences. Then we get a bunch of these embeddings here. We have another sequence encoder. This would be like attention layers, because this can be variable length. We can handle variable numbers of preference labels. And then we get our Z. We append the Z. Again, this is a fixed LLM, which is, so we're not training this to get our last token embedding. And then we do train an LLM decoder to then predict the reward from the Z and this. So this is kind of the architecture. It did take some, engineering to get this to work. But the nice thing is, at least on the data that we have, which again is using these preference data sets. So the users are like a user that prefers harmfulness and a user that prefers harmlessness, and a user that prefers helpfulness. So you can see how sometimes those diverge. We see, and this is like a synthetic data set where users prefer like different pets. Like some users both like dogs, but one prefers cats and one prefers bunnies or something. Like it's very synthetic. We see that unlike existing RLHF methods, which is VTL, or this DPL thing, which starts to talk about pluralistic alignment, Only our model is actually able to model these diverse preferences. And it's not 100%, but it's getting there. And so this would be the accuracy in predicting those preferences. And what we see is kind of nice. So what we're doing here is we're injecting noise into the preference labels by flipping the questions answered by each user. And we see that with various amounts of noise, we're still doing better than your BTL baseline, which kind of can't predict the preferences of a particular user. But if you inject 50% noise, now you just have no preference information left in your context. And we end up getting the same performance as the underlying vanilla BTL model. So what we would hope is that if you are trying to make predictions about a new user and they haven't given you any preference labels yet, you're getting the like average BTL model performance that you would have gotten anyway without doing this. But as you get more preference labels, you can customize the user more effectively. So you can like do the mode averaging thing by default, but then customize. To answer your embedding space question, this is the learned embedding space of the users preferring honesty and users preferring helpfulness. We see that the encoder is clustering users in the latent embedding space. So it is actually able to learn to separate users based on their preference labels. And that's how it's able to learn these different reward functions. So now the nice thing is you've got this like interpretable embedding space. So if you did this on a higher scale, like let's say you did this on Prism, you could say, you know, I'm going to plot the embedding space for a bunch of users and like color the users based on their demographics and see if it's actually learned to separate users that have certain preferences. Like you could imagine users from different cultures or something, like it could accommodate their different preferences. Okay, so this is a first work to introduce an end-to-end latent variable framework for LLM reward modeling, which is able to capture and adapt to diverse user preferences, enabling pluralistic alignment. In the future, the cool thing is this is probabilistic. So you get these uncertainty estimates and you get this interpretable latent distribution. Using that, you could do all kinds of things. One, you could enable an agent to stop if it's too uncertain about the user preferences rather than say the wrong thing. So if the agent is uncertain about what Z it is, and there could be vastly different preferences depending on the Z, maybe it just shouldn't answer rather than say something potentially wrong. You could also potentially detect adversarial or malicious users. If the embedding that you got for a particular user is like way off in embedding space, not near the training data, maybe this user is doing something adversarial and you should not be answering, right? You could find underrepresented user categories and ensure that the model accuracy is equally accurate for all of those categories. So I think this is pretty exciting. I'm gonna just wrap up and then I'll take all kinds of questions. So why should RL researchers get on the bandwagon of training LLMs with RL, just to wrap up? You might have seen on Twitter, some prominent RL researchers have said RLHF is not RL. I just attended this NSF RL conference, which is like 300 faculty from like top US institutions doing RL. And one of the most prominent RL researchers opened the workshop by saying, I'm not sure RLHF is RL. And I just think it's hilarious because it's like finally RL has had some actual economic impact and people are quick to gatekeep and be like, well, that's not really RL. And I think it's really foolish because like something is really happening with RL training of LLMs that's moving so fast and we're seeing such advanced capabilities. But the RL folks are like, no, I don't do that. And actually that whole workshop of like 300 faculty, there was like 2 people talking about RL training of LLMs, one of which was me. So I feel like the RL folks are not getting on board. The NLP folks are like really doing this. So I feel like this is a bit of the pitch to, if you like RL, why you should be doing LLMs. I think there's a lot that like classic RL has already explored in the robotic space that can be directly mapped to LLM space. So for example, a classic objective in RL is curiosity. So if you imagine like, we've actually seen this. So for chain of thought, right? There was this paper that was like multi-agent chain of thought helps because you just get more diverse chains of thought, right? That helps you find the better answer. So curiosity is saying, if I haven't yet found my sparse reward, which is whether I got the math question right at the end of my chain of thought, one good thing I could do as a proxy is just maximize the diversity or the, explore thoroughly the space of the world before I try to find my goal. And so this is a reasonable thing you could do in LLM space. In dialogue space, you could say, what should I be curious about? Well, it's actually the human user, right? And so we're actually working on a project at Google that's like, let's use the information gain on our model of the user as a reward to conduct the dialogue. So like if you think about, okay, you go to a conference, you're talking to a random person, what do you actually use as an objective in that dialogue? You don't necessarily need to get anything out of it, but you might just try to get to know the person. Like I might ask, oh, what do you do? What are you interested in? Right? That just helps me with understanding how to conduct a dialogue. So I think this is a reasonable thing to do. This is something I'm super excited about. So the whole idea that self-play or like online moral training of LLMs has not been done in the LLM era is bananas to me. So I'm working on this right now. We're trying to do zero-sum adversarial game to achieve safety guarantees. So basically you have an adversary. Look, all of the adversarial red teaming stuff basically trains against a fixed defender, right? Which is bananas because then the adversary just keeps finding the same attack over and over. So there's a bunch of papers that are like, let's give the adversary a diversity incentive so it discovers more diverse attacks. Well, guess what? If you set it up as an online game where the adversary discovers an attack and then the defender patches that hole and defends against it, then the adversary is forced to search for a new attack as part of the game. And so we can show that the Nash equilibrium of this game is basically that for all strings, all X that could be presented by the adversary, the defender achieves the maximum reward possible. So whether deep moral achieves the Nash is in question, but it's pretty cool to know that you could like set up a game where that's actually pointing. You would have a safety guarantee for LLMs, which I think would be very viable and interesting for a company like Google because they really don't like when their LLMs say something inappropriate. So yeah, I'm really excited about this. I think RL training of LLMs is the future. We should all get on board. This is my lab at UW that just started up last year. So we're going to year 2. If you want to learn more about the work in our group, you can check this out. We kind of span this space from like human AI to multi-agent research, including this learning from human feedback with language models. We do some instruction following stuff, all this stuff. But I'll shut up and take questions. Thanks.
I have a question just relating to the robot situation again, right? So if you have, let's say in a room, for a particular task, you have like 100 possibilities of placement for a particular object, but from the training data, so visually, like IRL, you see there's 100 possibilities of placement for a particular object, but in the training data, only a subset of that is represented. So you've got maybe half of it, like 50 places. Now, that's just purely because you're using, let's just say training data from like people just come up and just from human feedback, I guess. And this is not like a per user preferential feedback, I guess. I don't know how that's different, but maybe it is. But and then coming to like the adversarial topic that you talked about, which is like if a user potentially deviates from one of these 50 and goes, let's say 50 exists in one half of the room, which are represented, and the other half are not. User goes that way. So is there like a trade-off between security in terms of detecting adversarial attacks in this scenario versus what do you call it, like giving a user, I guess, or like serving a user according to their preferences better, right? So if a user would choose something that's just out of what's normal,
like I see. So if you say, okay, you're way off in embedding space, you look like no user I've ever seen before, should I actually shut down the model? That could be a design choice, right? I mean, it could be I would assume if you're OpenAI, you have a massive amount of scale of the data. So you probably have preference data covering like most reasonable users. So if you're OpenAI, you might say, okay, like this user is way off in space. I actually don't feel comfortable adhering to their preferences. It's like 0.00001% of users. Maybe I do want to stop. However, if you were like, I don't know, a startup that's just getting off the ground and you have barely any preference labels, you might not want to do that, right? It's kind of a design choice. So you might, I think what you were asking about is trying to go back to this picture, like what's my coverage, right? So imagine that I have only a very small data set and I've only covered users with preferences on this side of the room. If I now have a user with a preference on this side of the room, then I'm not able to accommodate that, but I shouldn't shut down the model, right? And so I guess I'll offer two things. Like one, if you do have a user that's like totally out of the realm of the preference data that you've covered, you shouldn't be any worse at catering to their preferences than the vanilla BTL model that we're already using, right? So it would give you the average of the users that are not like you, and that's not you, but that's what you would have gotten before. And then you can, but if you are within the distribution of users that it's seen before, but it just hasn't, it has high uncertainty, it hasn't mapped you yet. If you give it a few more labels, then it can better refine the Z and better adapt to you. Does that make sense? I don't know if that fully answers your question, but
yeah, it does. And then like, I guess, what would be the downsides of using, instead of just using collected data to that like collected labels to for placement, for example, for a robot, you use basically every single distinct point in the embedding space, and then use some sort of
yeah,
I guess like is it possible to place the object in this like some restriction in that way? Like you want to place an object on a surface that is, you know, elevated from the ground. So any place there's no surface above the ground, you can't place it. That sort of restriction. Then I guess how would that sort of input to the training data affect adversarial attacks, like adversarial attack detection, pretty much?
I see. Yeah, I mean, you might say like, okay, so at the end of the day, this whole reward model is like neural network based feature extraction. So you might say like there should be some level of generalization over that. So if all the preferences I've ever seen are to put objects on surfaces, and I've never seen someone put something on a floor, it's probably going to be able to generalize a little bit that like the surface matters. Or the height matters. And then if somebody says, I want something on the floor, and that truly was never in the training data, then it might detect that as like an erroneous user. But like, by the way, this is just like one suggestion for what you could do with this. I don't know if that's how you would want to engineer your system, but it's something that this would enable. So it's not like a, you have to do this, right? It's just like you could do that.
Right.
Yeah.
Thank you.
Hey, Natasha.
Hey.
High level question for you. So I think I do think it seems to be a good time to combine RL with LLM, especially basically a lot of people believe now how good the base models are can actually carry us a lot. I think even when I was doing my PhD, that's like 2017, like before
Nice.
17, right? There was discussion of RL used for NLP, and I think because I'm not a RL, by the way, but then in general, the concern we have is how do you model the reward? So RLHF is definitely one good thing, but I think you also touch in your talk, which is people have different preference, and also even say people have some similar preference, there are also many different way people will prefer one thing than another, like toxicity.
Yeah.
Like my group is particularly interested in creativity, so like people may prefer this because of the creativity and all that. So
Yeah.
in general, I think my always understanding and concern on the incorporate RL to large language model training is where do we find the reward? For example, actually, I was pretty surprised by the RLHF works so well, given that the original classifier, the trend, the reward model, I think the accuracy was 60% something.
I know, totally. Yeah.
Right? And but it worked. So I
Yeah.
just want this high level question of like from your perspective as RL experts, is there some way that we can get easy reward for training LLM? And also like when we're facing this world of there could be like multi-objective or many different ways that
Yes.
we may prefer something, like how should we go about it?
Yeah, so this is a very valid concern. If your reward function is hackable, your RL model will hack it, right? So I think you were mentioning about like pre-2017 RL for language models. I tried to put a nod to that. I'm sure I didn't cover everything. Maybe you had a paper I didn't cite, but yeah, like Blue Score is faulty. So if you over optimize on blue score, and especially if you don't do this KL constraint thing, then you're going to reward hack blue score, and it's going to be a problem.
Right.
So defining the right objective, it actually goes back to this like DeepSeek thing, which is the right incentives. If you provide it with the right incentives, it's going to optimize them. I'm actually not scared of multi-objective RL. If you provide 2 incentives, it will find the Pareto frontier if everything goes according to plan. And I think RL does work when you set it up correctly. So I'm not worried about that. But yeah, if you're doing like a soft thing like human preferences, then your reward model is inherently going to be a little bit faulty. So you may not want to overtrain against it, or you may want to have other things in place, which is like why the KL constraint comes into play. But I think there's a real series of papers to be written almost on like defining the incentives that may lead to better performance. And it's actually also why DeepSeek works well, right? Because they're using 0-1 success on the math problem.
Right. Some
So
of the
that's
more checkable,
verified.
like rules-based check,
Yeah.
and all that, right? But I
Exactly.
think that works good for mathematical reasoning. I can understand, but for the more like, language and or like a creative generation, I'm interested in. You
Exactly.
have this music generation. I think you probably also know what I'm talking about in terms of like how creative this piece of music
Yes.
are. It's not necessarily about the format. Like it's not necessarily about how much it follows the rule. Actually, it's about how much it breaks the rule, but in the right way, not like if you
It's like
completely break the
surprising and
garbage.
interesting.
Yeah, exactly.
Yeah, totally. Well, so we're actually working on a project. I don't know if you know Anna Huang at MIT. She was at Google before, but
okay.
we have a project called Real Chords that was at ICML this year. And the idea is to do RL training of LLMs to make big, like LLM size music generation models that you can jam with live. So you actually, and like, there's a lot of work on like human AI cooperation in the multi-agent space. So you're faced with a new human partner, you have no data from them. How do you cooperate with them? And you could port a lot of those ideas to the music cooperation setting. Like, how do we jam together? So then like, what is the right objective to do jamming? And we did a lot of work in that paper on how do you define better reward models for good music. And that was a lot of the contribution of that paper. But if you actually started collecting human data, you could do all like, this is why I was trying to pitch this little, I don't know if that came through super clearly, but like, I think some of the ideas in this early work on implicit cues in the conversation were interesting, and they didn't get followed up on because this technique was not as effective as like the modern RLHF technique. But like in music, you could imagine how long does the person play with the model? That's sort of a ground truth signal of how much they're enjoying it, right? It's like if they sign off, they're like, well, this was annoying. I don't like playing with it. If they keep playing, they come back, that's good. But then you get into the dangers of like, we know optimizing YouTube watch time with RL has problems. So you have to be careful. Like, what is the right incentive? So it's a very valid concern. Yeah.
Thank you.
Okay, so I saw a question in the chat. Is readability concerned in multi-agent training similar to the issues observed in DeepSeek R10 that require a cold start? How can we address things to ensure things remain readable and interpretable? So it's exactly what the DeepSeek paper showed, right? If you just do RL, it does like language mixing, it's trying to solve the math problem in Chinese. It puts code in its chain of thought. Like there's nothing constraining the chains of thought to be human interpretable. It's just trying to get to the right answer. So the incentive that you've set up is get the right answer. So that's why in the second part of the paper, they have to introduce, oops, we need to bring back everything of like, we need RLHF reward models, we need useful summaries, we need non-toxic chains of thought, right? So yeah, you might want to introduce other, we think of it as like reward shaping terms or other incentives to get the behavior you want, but why not? If you just introduce those incentives, it can optimize for those. So yeah, like I said, I'm not scared of the multi-objective part of it. Can we just use clustering to find closest modes for new users with no preference labels initially? Like clustering on their text itself, that could be cool. Yeah, we didn't explore that, but that could be an interesting idea for sure. Any other questions? I know we're a bit over time. Excuse me.
All right. I guess if no other questions, let us thank our speaker for this wonderful talk today. Thank you, Natasha, for coming in. Like, I really love the talk, and like, yeah, you covered so many different things, but are really, really relevant stuff. So yeah, thanks. Thank you.
Well, thank you so much for having me. Yeah, I'm really excited about this area. So if you have follow-up questions, please reach out. And I know I'm meeting with a few of you right now. So excited to chat.
So yeah, whoever's meeting with Natasha as well will just use the same Zoom here. So just join the Zoom and you can have a chat with Natasha. Yeah.
Awesome.
Thank
Thank you.
you.
Thank you.
Thank you.
Hey, Ashima, is that how you pronounce your name, Ashima?
Hi.
Hey, I guess there's some folks that didn't sign off. I don't know if you're comfortable with that, but
Oh, I don't mind. Before we start, I have a few logistical questions.
okay,
So I saw someone signed up for a one-on-one with you from 4:30 to 5 as well today
I can do that.
during the talk. Is that okay for you?
Yeah.
Okay, cool. That sounds good. Thank you so much for the talk. It was really nice.
Well, thanks for attending.
I'll start off with a little intro. I am Ashima. I'm a PhD student at UCLA. I'm advised by Professor Sadia Gabriel. She joins in summer of this year. So we are a fairly new lab. Most of my work has been, I'm currently exploring a couple of things, but most of it has been about safety and cultural value alignment, basically trying to make sure that LLMs serve humans as well as they can, instead of
Nice.
humans trying to serve LLMs.
Nice. Very worthwhile problem.
Yeah, so I was actually very excited that you mentioned the PRISM data set because I've just been obsessed with it
It's
when it
great.
came out. It is such a lovely initiative, and I haven't seen a lot of people try to use it in distribution preferences, or I don't think a lot of people have tried to use it. So it was nice to know that other people are thinking about the same.
Yeah. I mean, so if you want to like follow up on that, I don't know if you're trying to use it as well right now, or like what's your project? Yeah.
I've just been thinking about how to use it. I'm currently wrapping up some current projects. This is more of some brainstorming that we do in a lab for the summer. We're trying to
Nice.
do some projects for summer. But I've been thinking about, so I worked on a paper earlier, which was about trying to capture your reveal preferences in a different way. So usually right now for DPO type setup, hi Tanmay. You are